A short road trip east of Seattle will get you here, the channeled Scablands. And they're weird. There you'll find a gargantuan gorge in the land that drops steeply into a wide basin, as if a waterfall had once been there. 10 times the size of Niagara Falls. Fertile rolling hills abruptly end where a barren, rocky expanse begins. There's a massive wall of volcanic rock and mazes of channels that look strangely like a human brain. So, how did it get like this? I've got one word for you: water. Hi, I'm Sage, and this is Crash Course Geology. Water. We swim in it, wash our hands with it, and drink it out of obnoxiously large bottles. It's the stuff of life in Stanley cups. I didn't understand the craze until I saw yours, but I kind of get it now. And geologically speaking, it's kind of a big deal. Water has shaped Earth's landscape for billions of years. In teeny ways and in massive ones. And it keeps shaping it every second of every day, thanks to the water cycle, the constant movement of water between the oceans, glaciers, lakes, and rivers powered by gravity and solar energy. One of the main ways water shapes the Earth is through weathering, the process of wearing down rock over time. And that can look like a bunch of different things. Chemical weathering, for instance, occurs when chemical reactions caused by water or other substances, like acid that oozes from lichens, transform or destroys the minerals in rock. This is how we get karst landscapes, areas mostly made of carbonate rock, which dissolves when touched by a weak acid. And you know what's slightly acidic? Rain. As it falls and gets absorbed into the ground, it slowly dissolves the rock little by little, Swiss cheese style, over thousands of years. Then we end up with incredible caves like this in Slovenia. Water is also involved in physical weathering, a process where natural forces or living things break or wear away rock. In the case of water, it can do that through sheer brute force or by expanding where it freezes, like it does with this limestone in the North Pennine region of England. So weathering can make big changes to the landscape, as can its counterpart, erosion. Weathering happens when physical, chemical, or biological processes break or transform a rock. Erosion happens when gravity, wind, or water moves those broken off rock bits, known as sediment, somewhere else. Often erosion is caused by runoff, water that can't be absorbed by already soaked land, so it flows across the surface. Weathering and erosion join forces to create some amazing features, like these ones in Bryce Canyon National Park. A cap of hard rock on the plateau protects all the softer rocks below. So physical weathering by rain and snowmelt forms steep cliffs and narrow, rocky walls. Then, as temperatures rise during the day, water seeps into the cracks in the rock. As temps plunge below freezing at night, the water turns to ice, wedging the rocks apart. Eventually, the process breaks off chunks, creating windows in the steep, rocky walls. The roof of each window collapses, leaving these strange towers behind. And chemical weathering helps to round the rocks into a variety of bulbous shapes. These features go by several equally fantastic names depending on their location, including hoodoos, tent rocks, and fairy chimneys. You can also see the effects of weathering and erosion in the ways rivers change shape. Over time, a river carves a groove in the land, whether a V-shaped valley, a steeply walled slot canyon, or some other shape. But all that sediment cut from the terrain has to go somewhere. The river whisks that sediment downstream, the current slowing down as it enters a larger body of water or flows into a flat plain. Then the river dumps the sand in wetlands, called deltas, or triangle-shaped deposits, called alluvial fans. And rivers can change shape, too. You know how the Mississippi River looks like this on a map? That's just like its current vibe. This map shows where the river used to flow. This kind of change happens because, over time, water pushes sediments from one edge of the river to the other, forming meanders or curvy sections. And sometimes the river spills over, taking a shortcut and flowing in a straight line again. That creates an oxbow, a horseshoe-shaped lake. And there are about 1,500 oxbows in the lower Mississippi alone, more than anywhere else in North America. Now, let's head back to those cool caves in Slovenia. Remember how I said they're the result of rainwater getting absorbed into the ground? That's called groundwater. Sometimes you just gotta call it like you see it. Despite its humble name, groundwater is another major force in shaping Earth's landscape. But if you're picturing a subterranean kiddie pool, it's not quite like that. The sediment and rock beneath us have pores, little openings that can take in water like a sponge. Even a rock that seems solid has pores, including the influencer rocks, Dwayne. It's face-tuned, I promise you. Some rocks can hold a lot of water, while others can't. That depends on their porosity, or total amount of open space, and their permeability, or how easy it is for fluids to pass from one pore to another. Sediment in rocks that have both high porosity and permeability are called aquifers, pockets of water underground. Often, water only partially fills the pores near the surface, at the level where tree roots and hedgehogs hang out. Deeper down, groundwater completely fills the material's pores. This point marks the water table, the boundary where water-saturated ground begins. Water tables rise and fall for all sorts of reasons. The slope of the land, the amount of rainfall or snowmelt, the porosity and permeability of the rock, and even how the land is used. And not only can groundwater create incredible formations like those caves in Slovenia, but it can also lead to geological disasters. Sinkholes, for example, are common in karst landscapes. Groundwater can dissolve so much rock that the top layers collapse. Areas that experience tropical storms or droughts, followed by prolonged periods of heavy rain, are particularly susceptible to land sinkage, as well as areas where groundwater is overpumped for human use and not properly replenished. So, given time to work with, water can create some pretty wild features. But it doesn't always play the long game. Water can also change the Earth's surface fast. Remember the channeled Scablands? Those weird landforms in eastern Washington? Well, for a long time, we had no idea what created them, until a high school science teacher decided he had to know. Let's meet a couple folks who are geology rock stars to me. In 1909, when J. Harlan Brett started asking geologists about how the Scablands came to look like that, they didn't have an answer. So he became a geologist himself to figure it out. On the ground in Washington, he observed how huge these features were, all oriented in the same direction and made out of hard rock, as if they'd all been carved by a lot of water at once. From this evidence, he concluded that a massive flood, maybe the largest ever, had carved the Scablands in mere days, to which the geological community was like, no way. At that time, geologists believed that water only sculpts the land slowly, like through weathering and erosion. The idea that water could work so fast sounded ludicrous. So to prove his hypothesis, Brett had to figure out where all that water came from. He didn't find an answer until the 1940s, when a geologist named J.T. Pardee had a hunch about a prehistoric glacial lake in western Montana. He argued that thousands of years ago, the 2,600-foot-tall ice dam holding the lake had burst, unleashing a massive amount of water downhill at high speed. It would be like if all the water in Lake Erie and Lake Ontario burst at once. This was the missing megaflood that carved the channeled Scablands. It took a couple decades, but eventually, the evidence convinced even the loudest skeptics. But the case wasn't fully closed yet. Over the years, Brett's observed that some parts of the Scablands seemed more weathered than others. He updated his theory, saying that there had been at least 7 floods. And later research suggests that there were at least 80, spread out over 2,000 to 3,000 years, and maybe even earlier ice ages. So in a way, both Brett's and his skeptics were right. Water sculpted the channeled Scablands in ways both fast and slow. While floods of this size are historically rare, flooding on a smaller scale can still affect the landscape. Like the Yukon River in Alaska freezes over every winter and then thaws in the spring. That water causes erosion and melts a layer of frozen ground called permafrost, all of which affects the chemical balance of the Yukon River. And that's not to mention the damage to local communities. Water can also contribute to landslides. Weathering can wear down a slope over time. Then, when a heavy rainfall or snowmelt happens, or another destabilizing event like an earthquake or volcanic eruption, gravity can pull large amounts of rock down the slope all at once. Humans can also contribute to these disasters, but we'll get to that in later episodes. While we can't exactly predict when or if these kinds of events will happen, geologists can assess the likelihood using technologies like radar, electrical imaging, and computer modeling. The U.S. Geological Survey shares data with local governments and the public to prepare for and map floods. And different methods of flood mitigation are used all over the world, including a flood relief channel in Vienna, sponge cities that absorb water into the ground in China, and houses built on stilts by the indigenous Gayo people of Indonesia. The more geological information we gather, the better prepared our communities are. Everywhere it goes, water leaves its mark, from moving tiny grains of sand to carving massive landforms. Its effects can take thousands of years or mere moments. It hydrates our bodies, rains down on our homes, and shapes the very ground below us. Water is a force to be reckoned with. Next time, we'll learn about one of the most groundbreaking theories in geology: plate tectonics. See you then. Thanks for watching this episode of Crash Course Geology, which was filmed at our studio in Indianapolis, Indiana, made with the help of all these cool people. If you want to help keep Crash Course free, for everyone, forever, you can join our community on Patreon.